Dr. M.C. Sundaraja. He completed his undergraduate studies from Madurai Kamaraj University and went on to complete his master's in structural engineering from the same. He is a doctorate from Anna University and he's also done his postdoctoral fellowship at the Queensland University of Technology, Australia. He has more than 17 years of experience in the teaching profession and he has also published papers in 39 international journals, 7 national journals, 27 international conferences and 51 national conferences. He has so far published 124 papers in various journals. He went on to receive the Best Research Paper Award from IFERP, a unit of VVERT and NIRE on 4th April 2015. He has also received Outstanding Faculty Award from the Venus International Foundation Faculty Award, VIFFA, in the year 2015. Currently, Dr. M.C. Sundaraja is now working as an assistant professor in Tyagarajar College of Engineering, Madurai.
Welcome to UGC lecture series on B-architecture. In the previous lecture, we have seen the design of two-way simply supported slab, which is simply resting on 4 walls, which is having the room of size the same dimensions, and also which is having the dimension of 3.5 meter by 3.5 meter. In the case of 3.5 meter by 3.5 meter an effective room of size, for finding out or for assuming the thickness of the slab to find the self height, we have followed the separate codal provision in the case of deflection criteria. When the dimension of the room is up to 3.5 meter and the loading class is up to 3 kilonewton per meter square, we have followed the deflection criteria of the simply supported slab, that is L by overall depth ratio equal to 35, and it has been again further multiplied by 0.8 if deformed bars are used. But this lecture we are going to see the two-way simply supported slab which is resting on wall, which is having a dimension of, that is a clear dimension of 4 meter by 5 meter. So, in this it is the span of slab is somewhat more than 3.5 meters. So, we are going to follow the normal deflection criteria to assume the thickness of the slab to find out its self height. That is the deflection limit, that is L by D ratio equal to 20 for the simply supported slab for this case also. So, here in this lecture we are going to again, I have told you that a two-way simply supported slab, which is to calculate the total load acting on it as well as the bending moment using the IS codal provisions, and using the maximum bending moment we are going to find out the effective depth of the slab. And since it is as a two-way simply supported slab, we are going to find out the reinforcement for both the bending moment, and it has to be provided along both the direction. And finally, the depth, which has to be again checked with the limit state of serviceability, that is under deflection. Finally, we are going to see the reinforcement detailing of those slab. So, in this lecture we are going to see we are going to design the two-way slab, that is design a reinforced concrete slab for a room of size 4 meter by 5 meter, which is supported on 230 mm thick walls and subjected to a live load of 2.5 kilonewton per meter square. The load due to the floor finish is 1 kilonewton per meter square and the partition wall is 2 kilonewton per meter square. Use M20 grade concrete and Fe415 grade materials. As I already told you that here the size of room given in the problem is 4 meter. In the case of self height of the slab, we started assuming the thickness of the slab from the deflection limit. So, if the size of room is, that is less than 3.75 meter or 3.5 meter, and also the loading class is 3 kilonewton per meter square, we can assume the size of slab from the separate classification, that is separate classes of IS 456, that is L by overall depth ratio is equal to 35 and then further multiplied by 0.8. But in this case the size of room is different, that is it is in more than 3.5 meter. So, we can't follow that deflection criteria. Then the normal deflection criteria, that is for the simply supported slab, L by effective depth ratio is equal to 20. We are going to follow that for this room. Now, these are all the this is the table 27, which is used to find out the bending moment for the two-way slab. These are all the bending moment coefficient for the slab which is spanning in 2 direction at right angles for the simply supported slab, which do not have any adequate provision to resist corners at the corners from the lifting. Here effective size of room is 4.23 meter by 5.23 meter. That is, this is a size of room they have given in the problem. There is a 4 walls. Now the thickness of wall here it is 230 mm, and the dimension along this direction is 4 meter, and the dimension along y direction is 5 meter. So the effective dimension is, that is, Lx by Ly. So now we need to first check whether this is one way slab or two way slab. Ly by Lx is, which is equal to 5.23 by 4.23, which is equal to 1.24, which is less than 2. Hence it is designed as two way slab. So here we confirm this is the two way slab. Then first step, we need to find out the load acting on the slab, load calculations. First one, dead load. So here the dead load normally consists of self weight of the structure itself and weight of partitions and the weight of floor finish. So here they have given, and the live down on the slab is 2.5 kilonewton per meter square, floor finish is 1 kilonewton per meter square, partition they have given us, that is 2 kilonewton per meter square. Now first self weight of the slab. For self weight of the slab, first we need to assume the thickness of the slab from the deflection criteria, that is L by D ratio equal to 20. It is for simply supported slab. So D is equal to L by 20. For this case, we need to normally use the shorter direction, that is 4,230 divided by 20. 4,230 divided by 20 is equal to 211.5 millimeter. This is the depth of the slab, effective depth of the slab, and overall depth of the slab is 211.5 plus the clear cover for the slab is 15 if the diameter of the reinforcement is less than 12 mm, and next it is the cover, that is the diameter of the rod here I am going to use is 10, it is 231.5 millimeter. So the overall depth of the slab merely 235 millimeter, I need to use it. But based on my experience, I started using D is equal to 200 mm, that is 200 mm. Finally, we are going to check this depth of footing against flexure as well as for the subvisibility, that is under deflection. So self weight of the slab is 0.2 into 25, that is equal to 5 kilonewton per meter square, and the floor finish, that is weight of floor finish given in the problem is 1 kilonewton per meter square, and the weight of partition wall is 2.0 kilonewton per meter square. Now we need to calculate what is the total dead load acting on the slab. Total dead load W suffix D is equal to 8.0 kilonewton per meter square. This is total dead load, and the live load on the slab. Second one, live load on slab, that is denoted by W suffix L. It is given in the problem, that is live load on the slab is 2.5 kilonewton per meter square. Now total load on slab W equal to W D plus W L, that is equal to 10.5 kilonewton per meter square. So we have calculated the W. Next, second step, bending moment calculations. So since it is a two-way simply supported slab, the moment has to be calculated from the table 27 by using the moment coefficients for the respective value of Ly by Lx. Ly by Lx here it is, that is 5.23 divided by 4.23, that is equal to 1.24 that we have found at the beginning. So, this is the ratio that based on this one we are going to find out the moment coefficient in x direction and the moment coefficient in y direction. Since it is a two-way slab, we need to find out the bending moment along both the direction, and the reinforcement has to be separately found along the two directions, along x as well as along y direction. So, now here for 1.24 it is a value between 1.2 and 1.3. So, for 1.2, for 1.3 alpha x alpha y, that is alpha y alpha x is 0.084 for 1.2, for 1.3 it is 0.093, and for 1 alpha y for 1.2 it is 0.059, and for 1.3 it is 0.055. So, we need to find out alpha x and alpha y for the value of 1.24 by interpolation. So, linearly interpolate to find out the value of alpha x and alpha y for 1.24. So, here alpha x is 0.088 by interpolate these two value, and by interpolating these two value alpha y will be equal to 0.0585. Now, the bending moment along x direction is alpha x w Lx square, that is 0.088 into the total load acting on the slab is 10.5 into Lx, here it is 4.23 square, that is equal to 16.53 kilonewton meter. In similar manner, My, that is My again it is alpha y into w into Lx square, not Ly square, it is Lx square. So, here it is 0.0585 into w is 10.5 into 4.23 square, which is equal to 10.99 kilonewton meter. Now, next step, so we have found the bending moment along both the direction. Now, we are going to find out the effective depth of the slab for the maximum bending moment, and area of reinforcement has to be calculated separately for Mx and My. Effective depth of the slab, effective depth of slab, that is D. So, by assuming our section is a balanced section, assuming a balanced section and considering 1 meter width of the slab. So, the effective depth has to be calculated by equating mu maximum to mu limit. So, here mu maximum, m maximum here it is the x moment along x direction, that is mu maximum is equal to mu x, that is equal to 1.5 into 16.53, that is equal to 24.80 kilonewton meter. So, mu equal to mu maximum equal to mu limit, that is equal to 0.138 FCK BD square, where D is equal to square root of mu maximum divided by 0.138 FCK B, that is equal to 24.80 into 10 to the power 6. I convert kilonewton meter into Newton millimeter. 0.138 into 20 into 1000. The value here it is 94.74 millimeter. So, the depth of the slab is 94.74 millimeter, and the overall depth of the slab is 94.74 plus 15 clear cover, the diameter of the rod by 2, that is equal to and that is 20, that is 20 1 not sorry 111, that is 114.74 millimeter, which is less than the assumed value, that is d is equal to 200 minus 15 minus 10 by 2, that is equal to 180 millimeter. Is correct. So, which is less than 180 millimeter, hence safe against flexure. So, the depth of beam we have assumed which is safe against a flexure. So, I am going to keep d is equal to 200 mm and small d is equal to 180 mm. I am going to find out area of reinforcement. First, along x direction, that is along shorter direction. So, here mu x is equal to, that is we have calculated 24.80 kilonewton meter. So, here we have provided the depth which is greater than 114.7, automatically the section will be converted into under reinforced or singly reinforced section. So, to find out the area of reinforcement, we are going to use the expression for finding the singly reinforced section, that is area of reinforcement for singly reinforced section, that is 0.87 Fy AST into d minus 0.416 XU, where XU is equal to 0.87 Fy AST divided by 0.36 FCK B, that is 0.87 into 415 into AST divided by 0.36 into 20. We are normally considering 1 meter width of the slab, that is equal to 0.05 AST. So, this has to be substituted in the moment expression, then we need to find out the area of reinforcement. Mu here it is 24.80 into 10 to the power 6, which is equal to 0.87 into 415 into AST into d is 180 minus 0.416 into 0.05 AST. This is the expression. So, here when you use this expression and we get the quadratic equation, that is AST square minus 8653.64 AST plus 3.30 into 10 to the power 6 equal to 0. This is the one. So, here the AST we have found here by solving this quadratic equation, we are going 2 routes. Since it is a singly reinforced section, we are going to select the minimum route, that is AST required here it is 400 millimeter square. Now, we need to check this with the minimum AST, that is most important. So, minimum AST as per IS 456 is 0.12 percentage of gross area of concrete, that is 180, which is normally equal to, that is 216 millimeter square, which is less than 400 millimeter square. Now, adopt AST require along x direction is 400 millimeter square. Now, we need to find out the spacing of reinforcement by assuming or by using 8 mm diameter bar. So, I am using here it is 10 mm, 10 mm diameter bar. I am going to find out the spacing of reinforcement. Normally, the design of slab is based on 1 meter width. So, the spacing of reinforcement should also be found against 1 meter width of the slab, that is 10 square into 1000 divided by 400, that is equal to 196.35 millimeter. Now this spacing has to be again checked with the minimum spacing. Check with the maximum spacing, not minimum spacing, maximum spacing. So maximum spacing of the parallel main reinforcement is that should not exceed 3 times the effective depth of the slab or 300 mm, whichever is less. So 3 into 180, that is equal to 0, 2, that is 540 mm. So the minimum value is 300 mm, which is greater than 196.35. Hence adopt 8 mm diameter bar at 175 mm center to center. This is along x direction. So AST provided along x direction is pi by 4 into 10 square into 1000 divided by 175 mm, that is equal to 948.80 millimeter square. Sorry, 448.80 millimeter square. In similar manner, we are going to find out the reinforcement along y direction. So along y direction, the MUY is equal to 1.5 into 10.99, that is equal to 16.485 kilonewton meter. So here also I am going to use the same expression, that is MUY is equal to MU equal to 0.87 FY AST into D minus 0.416 XU. Normally XU here we have already found, that is equal to 0.05 AST, that has to be substituted, that is 16.485 into 10 to the power 6, which is equal to 0.87 into 415 into AST into 180 minus 0.416 XU. The XU here it is 0.05 AST. So by solving the quadratic equation from this expression, I get the minimum root as 262.17 millimeter square as the AST required. So here I am using 8 mm diameter bar. I am using the 8 mm diameter bar. Spacing of bar I get here it is pi by 4 into 8 square into 1000 divided by 262.17, that is equal to 191.73 millimeter. So provide 8 mm diameter. So this spacing is within the maximum spacing, that we have seen in the reinforcement for MX direction, that is x direction, 8 mm. So here I am providing 8 mm diameter bar at 175 mm center to center. Now I am going to check this with the depth of the section against deflection before drawing the reinforcement detailing of the slab. Check for deflection. Check the depth for deflection, that is I am using L by D ratio equal to 20, that has to be again modified by multiplying with the modification factor. This has to be found from the figure 4. Figure 4 shows the modification factor versus percentage tension reinforcement. That is why I am finding percentage tension reinforcement is AST provided divided by B into D, that is equal to. So here we need to put the maximum AST provided, that is 448.4 divided by 1000 into 180, that is equal to 0.25 percentage, and D is equal, that is modification factor, here it is we got is 1.9 for the stress of Fs is equal to 214.53 Newton per millimeter square. So D here it is L divided by 20 into modification factor, that is equal to 111.32, which is very less than 180 mm. This is safe, but it leads to uneconomical. When compared 180 mm with the 111 mm, 111 mm is very less than 180 mm. So this section leads to uneconomical. So we can again redesign the section by reducing the size of the section. Now we are going to see the reinforcement detailing. Reinforcement details. So this is a simply supported slab. which is resting on the edges. So, here in the case of two-way simply supported slab, the reinforcement along both the direction is the main reinforcement. If you take this as the LX, that is 4.23 meter, along 4.23 meter this reinforcement is 10 mm at 175 mm center to center, and this reinforcement, that is the reinforcement perpendicular to the direction of 4.25 mm length, that is along 5.23 mm, that reinforcement is 8 mm dia at 175 mm center to center. In this case, we need to also design the torsion reinforcement. Torsion reinforcement is normally 3/4 of the main reinforcement, that is which has been used in the direction 448.8 mm square. That has to be provided along Lx by 5 and Ly by 5 at the corners to resist the lifting up of the slab or to resist the torsion. So, here this is the torsion reinforcement. In addition to this, we need to provide. So, this is the plan view. So, this is the room. We are having a wall on 4 sides. So, we need to provide the torsion reinforcement in addition to the main reinforcement, that is in terms of 4 layers, that is along x as well as y direction, that is 2 layers at the top and 2 layers at the bottom. That reinforcement is normally 3/4 of the maximum reinforcement that is used in the x direction. So, here this is Lx by 5 and this one is Ly by 5. In addition to this main reinforcement, the corner reinforcement has to be provided in the case of simply reinforced two-way slab, which do not have any adequate provision to the torsion at the corners. Now, we come to the end of this lecture. Let us summarize this lecture. That is, in this lecture we have seen and worked example which have been carried out to design the slab, that is two-way simply supported slab, which do not have any adequate provision to resist the torsion, and also we have seen the detailing of reinforcement in this slab. Next, in connection with this lecture, the additional questions are: design a two-way reinforced concrete roof slab for a room of size 5 meter by 6 meter subjected to a live load of 0.75 kilonewton per meter square. So, here this is for a residential building which is used to support a load of 0.75 kilonewton meter at the roof, which do not have any adequate access. Next, the live load on the load due to the floor finish is 1 kilonewton per meter square. Use M20 and Fe415 as materials. The second problem: design the reinforcement required for two-way slab which do not have any adequate provision to prevent the lifting of corners. The clear dimension of the room is 6 meter by 6 meter. It is supported on 230 mm thick wall. Live load on the slab is 1.5 kilonewton per meter square. Consider other deck loads also. Use M20 and Fe415 as materials. In connection with this lecture, the references are the plain and reinforced concrete code of practice, that is IS 456-2000, and another code of practice to find out the load for the buildings and structures, that is IS 875-1987, and another important code book to know the reinforcement detailing for the concrete structures, that is SP 34 and 1987, and the books are the reinforced concrete designed by S.N. Sinha, which is published by Data McGraw-Hill Publishing Company, New Delhi. Then another book which is written by S.O.K. Jain, that is Reinforced Concrete Limit State Design, which was also published by Nemchand and Brothers, Roorkee. Thank you very much.